Hello and welcome back to Start Learning Logic, now with part 2. And first I want to thank all the nice people on Steady or PayPal who support this channel. Now, to refresh your memory, last time we learned the meaning of logical statements and we used the names A and B to denote them. And then we have seen that we can formulate new logical statements with the negation and the conjunction. These two new symbols we called logical operations, and this one was the not operation and this one the and operation. Now, if you have such a formula with logical operations, the original statements A and B are often just called logical variables in this case. So you see we have a lot of vocabulary, which is in the end maybe not so important. The important thing will be that you understand all the symbols we use. Okay, then let's continue introducing more symbols with logical operations. The next one is the so-called disjunction, also defined for two logical statements A and B, and it's similar to the AND operation here because it's the OR operation. The symbol we use here is the flipped one, so just a V. As in the last video, we can define the symbol by writing down the truth table. The disjunction should be true when at least one of the two constituents is true. So we have true here, and also in the first line because both of them are true and we don't have an exclusive OR here. However, when both of them are false, we have a false. Similar to the conjunction, you can also visualize this with a circuit and a lamp. In this case, the two switches just have to be parallel. Now, having these logical operations, we can combine them in a lot of ways to get out new logical statements. Therefore, the natural thing to do is writing down a truth table for such a new combination. So let's consider a simple example here. What about not A or A? Here you see what we usually assume is that the not operator binds closest, therefore we don't need any parentheses here. Now in this example our combination just has one logical variable, which means our truth table just needs two rows. Okay, so let's fill that in. We know that not just flips the truth values. And now the OR just needs one true, so we have a true here and a true here. Now you see, this combination always gets you a true statement out, no matter what the truth value of the input A was. In logic, we call such a thing a tautology. So it's a combination of logical operations and logical variables that is always true, no matter what the truth values are of the logical variables that are contained in the formula. Of course, this was a simple example. You could have many different logical variables in the formula, but then the truth table would be much bigger. Of course, knowing which combinations are tautologies is very helpful because you always can substitute this combination then with just a true. Now related to that is the notion of logical equivalence. It also tells you when you can substitute one formula with another. We call two logical statements, so combinations as we had before, logically equivalent if the truth table looks the same for both. More concretely, you have to look at all possible assignments of truth values for the logical variables that are included in both formulas. And if you get the same output for both formulas, we call them logically equivalent. Okay, so it looks like a reasonable term, but to understand it, I think we should look at an example. Here I want to consider A or B with a not in front, and also not A and not B. So please keep in mind we need parentheses here, but not here. But of course, if you want, you are allowed to use them here. Okay, then let's do a large truth table. Of course, we need here our inputs A and B and the outputs on the right hand side. Then in the next step we can fill in all possible combinations of the truth values of the logical variables. Afterwards, we have to think what are good intermediate steps to reach our result on the right hand side. Here, for example, I would say we calculate first A or B. For this, we already know the truth table. We have true, true, false. And then we just have to use the negation, which switches all the truth values. So we have false, 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 true. So now we finish with the first one. And for the second one, I would say we first write down not A and afterwards we write down not B. Okay, filling this in was not so hard because we already know how to do this. And now for the last step, we have to use the AND operator. In the first line we have false and false, so this is false. Then we have false and true, still false. Then we have true and false, still false. And in the last line we have true and true, which is true. And there we have our result. The truth values for both combinations match completely. In other words, they are logically equivalent. And the symbol we use for this is this doubled arrow. For you, this means if you have a large formula as a logical statement where you have this part inside, you can easily substitute this with this one without changing the truth value, and also the other way around. So the logical equivalence is what you can use to simplify a complicated expression step by step. Of course, we will see examples of this, but first I want to use the next video to show you more logical operations. So I hope I see you there and have a nice day. Bye!